What if the strangest thing ever found inside the world's greatest physics experiment was not a new particle at all, but a crack in the idea of time itself? For decades, the equations that describe every particle and every force we know held so perfectly that some scientists quietly stopped looking for surprises. Then the surprises came anyway. Small ones. A measurement leaning where it should have stood straight. The same lean, in the same place, again and again, in more than one machine, refusing to be explained away. Follow that lean far enough, and it stops being a story about particles and becomes a story about you, about whether the single solid reality you're standing in was ever really single at all, or whether it has quiet neighbours we were never built to see. Where does a crack like that actually lead? Get comfortable and let your breathing slow. Subscribe if you have not already, and stay with me tonight, because the trail from that one small crack runs through the deepest questions physics knows how to ask, and it ends somewhere unexpectedly gentle. Let's get into it. Part 1. The Machine and the Silence. Silence. 17 miles of tunnel coiled beneath the border between Switzerland and France, buried deep enough that the seasons never reach it. Down there is no weather, no daylight, no sense of the world turning overhead. There is only the machine, and the machine is enormous. It is heavier than the Eiffel Tower, and it has been cooled to a temperature colder than the empty space between the stars, colder than almost anywhere in the known universe outside of a laboratory. It fires protons around that ring at 99.99% of the speed of light, and then it steers two of those beams into each other and slams them together roughly 1 billion times every second. Each collision crushes an enormous amount of energy into a space smaller than a single proton. For a fraction of an instant, far shorter than anything your senses could register, the impact recreates the conditions that existed in the first millionth of a second after everything began. Particles that have not existed since the birth of the cosmos flash into being, live for less than 1/trillionth of a second, and then shatter into fragments. And detectors the size of apartment buildings are waiting to catch those fragments. They measure the angle of every shard, the energy of every trace, the lifetime of every ghost that flickered through the collision point and vanished. You do this 1 billion times per second, for months at a stretch, and out of that storm of data you build a picture so sharp that you can predict the outcome of the next collision before it happens. That is the strange thing about this kind of physics. It is not guesswork. It is not a rough sketch of how nature behaves. It is a set of predictions so precise that they start to feel less like science and more like prophecy. Physicists did exactly this for decades. Every prediction held. The accuracy reached 11 decimal places. Try to feel the size of that number for a moment. If you predicted the distance from New York to Los Angeles with that precision, you would be off by less than the width of a single atom. Not the width of a hair, not the width of a grain of dust, the width of one atom, across an entire continent. That is how well the equations matched the machine. Some physicists understandably stopped looking for surprises. The mathematics had swallowed everything the collider could throw at it. When your theory is right to 11 decimal places, you begin to suspect there is nothing left to find. Then, around the year 2021, the detectors started returning numbers the equations could not produce. And here is the part that matters. It was not an explosion of impossible particles. It was not some dramatic failure, some alarm blaring in the control room, some result that announced itself. It was a quiet tilt. Certain measurements sliding away from the predicted values by fractions of a percent. If the tilt had been random, you could have shrugged and ignored it, the way you ignore static on a radio. But it was not random. It appeared in the same measurements. It leaned in the same direction. It showed up in run after run, month after month, and it never corrected itself. So the physicists did what physicists always do. They assumed they had made a mistake. They recalibrated the instruments, checking every sensor, every wire, every assumption baked into the hardware. The tilt stayed. They rebuilt entire sections of the analysis from scratch, suspecting the error lived in the software rather than the machine. It stayed. They changed the statistical framework, the very mathematics they used to decide whether a signal was real. And still, it stayed. You know what a hairline crack in a foundation wall looks like. You press your finger to the concrete and feel the gap, and it is so small it seems absurd to worry about. It is too small to matter, But every spring, when you check it again, it is a little wider. That is what this data looks like right now. When physicists confirm a prediction, they hold press conferences, they put out papers with triumphant titles. But when they find a crack they cannot explain, they go quiet. And right now, they are very quiet. They are quiet because the crack runs through the most successful theory human beings have ever built. Stay with me here, because to understand why a fraction of a percent has some of the smartest people on the planet losing sleep, you have to understand what that fraction of a percent is threatening. And it is not a small thing. It is the foundation underneath the foundation. It is the map we used to build the machine that is now quietly redrawing the map. Part 2. The most successful theory ever built. 3 generations of physicists hammered the standard model of particle physics together over roughly 50 years. It is not one idea. It is the accumulated work of hundreds of people, thousands of experiments, a slow assembling of a single map that describes every particle we have ever found, every force except gravity, and every way that matter and energy touch each other across the observable universe. When you break a table down into wood, and the wood into fibers, and the fibers into molecules, and the molecules into atoms, and the atoms into the particles inside them, the standard model is the document that describes what you find at the bottom. It is the closest thing we have to the blueprint of physical reality. And it works. It works almost unreasonably well. It predicted the existence of a particle called the Higgs boson 2 full decades before any detector was powerful enough to catch one. Think about that. Physicists wrote down, on paper, that a certain particle had to exist, that it had to have certain properties, and then the rest of the world spent 20 years and billions of dollars building a machine capable of checking. And when CERN finally pinned the Higgs down in 2012, the mass of the particle landed within 1% of the prediction. The map had described a mountain no one had ever seen, and when we finally climbed to that spot, the mountain was there. It is hard to overstate how good the standard model is, so let me put it in terms your body can feel. There are around 200 numbers that describe every particle we have ever detected, their masses, their charges, the strengths with which they pull and push on one another, and the model ties nearly all of them together into a single interlocking framework. Change one, and the others shift, the way tugging one thread pulls the whole weave. For 50 years, every time a new experiment measured one of those numbers more precisely, the model was already waiting there with the right answer. Physicists have a quiet, almost superstitious respect for a theory like that. You do not get to be right by accident 200 times in a row. When something is that reliable for that long, you stop thinking of it as a description of reality and start thinking of it as reality itself. Which is exactly why the smallest disagreement, in exactly the wrong place, feels less like a measurement error and more like a betrayal. Engineers trusted that map enough to bet the entire machine on it. When they designed the collider, they used the standard model to calculate how much radiation the tunnel walls would absorb, and then they poured the concrete to exactly that specification. If the model had been wrong by even 0.5%, the walls would have failed. The collider would have cooked itself from the inside, an accident measured in billions of dollars. But the concrete held. The model held. Everything held for so long that the map and the territory became the same thing in the minds of the people who used them. This is a very human trap, and it is worth naming, because it is the whole reason the current moment is so unsettling. You stop questioning a clock that has never lost a second. You set your surgeries by it. You launch rockets by it. You build your entire civilization on the quiet assumption that the next tick will land exactly where the last one did, and the one after that, forever. You do not stand over the clock waiting for it to fail, because it never has. Its reliability becomes invisible. It becomes the floor you stand on rather than an object you examine. And then, one morning you notice the second hand dragging. Not by much. Not by enough for anyone standing across the room to see. But you happen to have built a machine precise enough to count the microseconds, and the microseconds are off. The clock still looks fine from a distance. The tick still sounds right to the ear. But something inside the mechanism has shifted, and you cannot see what, and, worst of all, you do not know whether it is getting worse. That is the standard model right now. The predictions still hold for the overwhelming majority of what the collider produces. If you fire protons together and ask the model to describe the ordinary debris, it answers correctly, again and again, the way it always has. But in specific corners of the data, In the places where the machine pushes energy to its very highest concentrations, the map has started to peel away from the ground beneath it. And here is the crucial detail: the ground moved. The map did not. Let me say that more carefully, because it is the hinge of everything that follows. A theory is a map of reality. For 50 years, wherever we looked, the map matched. Now, in a few very specific places, reality is doing something the map does not describe. And when that happens, there are only two possibilities. Either we drew the map slightly wrong, and there is a correction we have not found yet, some missing particle or force that will patch the gap and restore the old picture. Or the map is fine, and reality itself is stranger than the map was ever built to capture. Those are very different futures. The first is a footnote, the second is a doorway. And to figure out which one we are standing in front of, you have to look at exactly where the ground first began to shift. It shifted, of all places, under a single, unstable, almost unbelievably short-lived particle, and it shifted in a direction that pointed at something no one expected. It pointed at time. Part 3. The particle that leaned. The ground shifted first under a particle called the B-meson. It is unstable, which is a physicist's polite word for doomed. It comes into existence, it lasts about 1.5 trillionths of a second, and then it falls apart into lighter pieces. That is its entire life. But the standard model does not just say that it falls apart. It predicts exactly which pieces it becomes, exactly how often each outcome occurs, and exactly at what angles the fragments fly away. The decay of a B-meson is supposed to be one of the most tightly scripted events in all of physics. There is a detector at CERN called LHCb, built for one purpose above all others, to watch this particular kind of process with a precision no other instrument on Earth can match. And it noticed something. When a B-meson falls apart, it can produce, among other things, either an electron or a heavier cousin of the electron called a muon. Now, the muon is essentially an electron that weighs about 200 times more. In every other respect, as far as we have ever been able to tell, they are the same, and the force that drives this decay is supposed to be completely blind to mass. It does not know, and should not care, that the muon is heavier. It should produce electrons and muons at exactly the same rate. 50-50. No preference. This principle even has a name, lepton universality, and for decades it was treated as one of the bedrock symmetries of nature. The detector found a preference, slightly more electrons, slightly fewer muons, and this is where the temperament of a good physicist matters, because a single result like that means almost nothing. You run the experiment once and the tilt could be noise, a statistical accident, the kind of thing that happens all the time when you're measuring fractions of a percent. So you run it 100 times, and the tilt has not moved. You run it 1,000 times, and it is still leaning in the same direction, still favouring electrons, still refusing to scatter the way random noise scatters. Noise cancels itself out, it wanders, it does not lean. But something was pressing its thumb on the scale, gently, persistently, and the thumb did not belong to the standard model, and the pressure pointed somewhere specific. It pointed at time. To understand why, you have to know that there was an older version of this tilt, one that two physicists named James Cronin and Val Fitch had caught more than 60 years earlier. In 1964, they were studying particles and their mirror image partners, the antimatter versions, and they proved something that genuinely rattled the field. Matter and antimatter do not perfectly mirror each other when you reverse the flow of time. The equations at that point demanded perfect symmetry. Run the universe forward, run it backward, and it was supposed to look the same either way, like a film that plays identically in both directions. The particles broke that rule. The universe, it turned out, has a faint but real preference for one direction of time over the other. It was a tilt so slight that it took a Nobel Prize just to measure it. Now, the standard model did not collapse under that discovery. It is a resilient thing. It absorbed the tilt. It filed the asymmetry under a specific mathematical mechanism, gave it a home, and moved on. For 60 years, that container held everything. But the new data pouring out of LHCb is pouring more asymmetry into that container than it was ever built to hold, and here is the connection that should make the back of your neck prickle. The tilt Cronin and Fitch found in 1964 and the tilt that LHCb is finding now are not two separate problems. They may be the same fracture, measured 60 years apart, at two different depths, and measured now, at higher energy and finer precision, it is deeper than it was. Sit with the shape of that for a moment. A crack was noticed in the 1960s. Everyone agreed it was small, filed it away, and built the rest of the house on top of it, assuming it was stable. And now, with better instruments, we go back and press a finger to that same crack, and it has widened. The house is the same house. The wall is the same wall. But the gap that we told ourselves did not matter has grown, and it has grown in the one direction we least understand. Because of everything in physics, of everything we have ever measured and modelled and mastered, time is the thing we understand least. And the fracture does not stop at the B-meson. It shows up somewhere else too, in a completely different corner of the machine, and that is where the pattern stops looking like coincidence. Part 4. 3 cracks. Pointing the same way. Deeper in the collision records, spread across years of data from 2 independent detectors named Atlas and CMS, something stranger is happening. It flickers. Since roughly 2015, both of these detectors have periodically caught bursts of excess events at specific energy levels. More particles coming out of certain collisions than the standard model says should exist. On the graphs the physicists stare at, these show up as bumps, a flat line running along at the expected value, and then, at a particular energy, a little hill where there should be nothing at all. A bump means something appeared at an energy where the map says the ground is empty. There is a very strict rule in this field for when a bump becomes a discovery. It has to cross a statistical threshold called 5 sigma. In plain language, 5 sigma means there is less than 1 chance in 3.5 million that you're looking at random noise. That is the standard. That is how sure you have to be before you're allowed to say you found something. It is a deliberately punishing bar because physics has been fooled by hopeful bumps before, and the field has learned to distrust its own excitement. This has happened, and it is worth remembering, because it is the honest counterweight to everything exciting in this story. There have been bumps in the past that climbed to 3 sigma, sometimes higher, that made a whole field lean forward in their chairs, that spawned hundreds of hopeful papers within weeks. And then more data arrived, and the bump melted away like frost in the sun, and it turned out to be nothing but the statistics doing what statistics do. Physicists still talk about those episodes, a little ruefully, the way you might talk about a time you were sure you heard someone call your name in an empty house. So when I tell you these current bumps are interesting, I am not telling you they are real particles. I am telling you they have a property that the old false alarms did not have. The false alarms appeared once and vanished. These keep coming back to the same energy in more than one machine. That is the detail that separates a trick of the light from a shadow cast by something solid. These bumps do not reach 5 sigma. They climb to 3 sigma, sometimes 4, close enough to see clearly, close enough to make a room go quiet, and then they sink back down with the next round of data. And then, months later, they reappear, at the same energy. That last detail is the one that will not let physicists sleep. The safe, boring, responsible explanation for any single bump is simple statistics. If you search through enough energy ranges, you will find occasional bumps by chance alone, the same way that if you stare at enough clouds you will eventually find one shaped like a face. That is true, that is real, that is the null hypothesis, and it deserves respect. But chance does not come back to the same address. Random noise, by its nature, does not remember where it appeared last time. It does not synchronize. And yet these bumps keep flickering into existence at the same energies, and they keep doing it across 2 machines built by different teams, in different caverns, running different software, checking each other's blind spots. A bruise that heals and comes back in the exact same spot is not a bruise. It is a sign that something underneath the skin keeps breaking in the same place. So step back and look at the whole pattern at once, because it is the pattern, not any single piece, that is the story here. You have the B-meson tilt that refuses to scatter. You have a time asymmetry that has been quietly growing for 60 years. And you have bumps that keep flickering at the same energies in 2 independent detectors. 3 anomalies, from 3 different corners of the machine, discovered by 3 different lines of investigation. And when you lay them side by side and ask what they have in common, the answer is unnerving. Every one of them involves how particles behave across time, not across space, not across distance, across time. The asymmetry between matter and antimatter is a statement about the direction of time. The B-meson's preference is tangled up in that same time reversal question. The bumps sit at the energies where those effects concentrate, and every one of them gets stronger the harder the collider pushes. and every one of them sits at energies where the conditions inside the collision begin to resemble the first moments after the universe was born, the era when whatever rules we live under were still being set. That is the thread. Something about time, at those energy scales, does not work the way you were taught it works. And I want to be careful and honest with you here, because this is the exact point where a channel could lie to you and tell you the answer has been found. It has not. These anomalies are real, but they are not yet discoveries. Each one, on its own, could still evaporate with more data. That is genuinely possible, and any honest physicist will tell you so. But taken together, pointing in the same direction, at the same feature of reality, they are enough to make serious people go back and question the single most basic assumption underneath all of physics, the assumption about time. And it turns out we have been making that assumption quietly and confidently for 300 years. Part 5. 300 Years of a Single Assumption. For 300 years we built everything on a single assumption about time. Isaac Newton wrote it directly into his equations as a constant. Time, in Newton's universe, was a kind of universal metronome, ticking away at the same rate everywhere, for everyone, forever, regardless of speed, regardless of gravity, regardless of the mass of the nearest star. It was the stage on which everything else happened, and the stage itself never moved. Bridges stood on that assumption, cannons fired on it, ships crossed oceans using mathematics that quietly took for granted that every clock in the universe kept the same beat. It was so obvious that no one thought to question it, in the same way that no one questions the ground until it moves. In 1905, a 26-year-old patent clerk in Bern, Switzerland, proved that the assumption was broken. His name was Albert Einstein, and he showed that time is not a fixed universal metronome at all. Time stretches when you accelerate. It compresses when you sit inside a gravitational field. Move faster, and your clock runs slower than the clock of someone standing still. Sit closer to something massive, and your clock drags behind the clock of someone farther away. Time, Einstein showed, is local. It is personal. Your now is not the same as everyone else's now, and I know how that sounds. It sounds like a curiosity, a mathematical trick that only matters at impossible speeds, near black holes, in places no human will ever visit. But you use this fact every single day, and you would be lost without it, quite literally. The GPS satellites circling the Earth right now carry atomic clocks, and those clocks tick faster than the clocks on the ground beneath them, faster by about 38 microseconds per day. That sounds like nothing. It is nothing to a human nervous system, but if the software running your phone did not correct for that tiny gap, the errors would pile up so fast that your navigation would place you about 11 kilometers away from where you actually stand before lunchtime. Every time you follow a blue dot across a map, you are relying on the fact that time moves at a different speed in orbit than it does in your pocket. Time on the roof of your building runs faster than time in the basement. The difference is far too small for your nerves to register. It is not too small for a cesium clock, and it is not too small to matter. Let yourself sit inside that for a moment, because it is one of those facts that is easy to say and almost impossible to truly believe. Right now, as you listen, the clock at the top of the tallest building near you is running faster than the clock in its basement. Not because of anything mechanical, not because one was built better, because the floor of the basement sits a little deeper in the Earth's gravity, and gravity slows time down. If you took two perfect atomic clocks, synchronized them, put one on a high shelf and one on the floor and left them for years, they would drift apart. The one on the shelf would tick ahead. This has actually been measured in ordinary laboratories, with a height difference smaller than a person. The people living on the upper floors of a tall building are, in the most literal and measurable way, aging a few billionths of a second faster than the people on the ground floor. Time is not a single river carrying everyone along at the same speed. It is a landscape of countless little currents, each running at its own rate, and you spend your whole life inside your own private current, never noticing that the person across the room is, ever so slightly, living in a different one. So Einstein did not merely prove that time bends in some abstract sense. He proved something much more disturbing. He proved that time is a physical thing. It is not the empty backdrop Newton imagined. It responds to mass and to velocity the way a sheet of rubber responds to a fist pressing into it. It deforms. It has shape. And this is the sentence to hold on to, because everything that follows in this story unfolds from it. If time has shape, then it is a thing you could, in principle, look at all at once, from the outside, the way you can look at the whole shape of a landscape from an airplane instead of experiencing it one footstep at a time from the ground. You never get to do that, of course. You're stuck inside time, walking through it one moment at a time, experiencing it from a single point, but the mathematics does not have that limitation. The mathematics can hold the whole shape at once, and there was a mathematician who did exactly that, who took Einstein's equations, laid the whole shape of time out flat on the table, and looked at it as a single object. What he saw was so strange that Einstein himself resisted it at first. It quietly dismantled the most basic story you tell yourself about your own existence, the story that you are moving forward through time, that the past is gone and the future has not happened yet. That mathematician was Einstein's former teacher, and what he found is where the ground really starts to give way beneath your feet. Part 6. The Worm Inside the Apple. Hermann Minkowski took Einstein's equations and rebuilt them as geometry. Instead of treating time as something that flows alongside space, he fused the two into a single four-dimensional object. Not time running next to space, keeping pace with it. One object, four coordinates, length, width, height, and time, woven together so tightly that pulling them apart breaks the mathematics. He called it space-time, and the name has stuck ever since. In a famous lecture he declared that space by itself and time by itself were doomed to fade away into mere shadows, and that only a union of the two would survive. He was not being poetic. He was describing what the equations actually required. And in this geometry, time is not a flow. It is a direction. You can point north, you can point up, and you can point toward next Thursday. Mathematically, in Minkowski's picture, those are the same kind of operation. Direction in space, direction in time, the same underlying grammar. Now follow where that leads, slowly, because it is easy to say and very hard to feel. If next Thursday is a direction the same way north is a direction, then next Thursday is a place. It exists, not will exist, exists. Right now, at a specific set of coordinates, in exactly the way that a city on the opposite side of the planet exists right now, even though you are not there, even though you cannot see it. You cannot see that distant city because you are in the wrong place to see it, not because it is not there. Minkowski's geometry says the future is the same. You cannot see next Thursday because you are in the wrong place along the time direction, not because it has not happened. And everything behind you still exists too. Yesterday did not dissolve when you finished living it. Your 10th birthday did not vanish. In this picture they are sitting at their own coordinates in the four-dimensional block, fully intact, every candle, every face around the table, as real as the ground you're standing on. This idea has a name. Physicists and philosophers call it the block universe, and it is not fringe. It is the most straightforward reading of the mathematics Einstein and Minkowski handed us. I want to be honest that it is an interpretation, not a proven fact. There are serious thinkers who argue for other pictures, where the future is genuinely open, and only the past is fixed. But the block universe is the reading that falls out of the equations most naturally, the one you have to work hardest to avoid. Here is what it does to the story of your life. You've been thinking of your life as a journey, a line moving from the past into the future, a single point of now travelling along it. Minkowski's geometry says it is not a line being drawn. It is a line that is already there. Imagine a worm burrowing through an apple. The worm feels like it is moving forward, carving a tunnel as it goes, creating the path with its own motion. But cut the apple open, and the tunnel is already there, whole, from entrance to exit, every inch of it existing at once. The worm did not create the path by moving through it. The path is the shape of the worm's whole existence, laid out in the flesh of the apple. The worm only experiences it as forward motion because it is trapped inside, reading one position at a time, unable to see the whole fruit, and you are trapped inside. Your life, in this picture, is not a sequence of moments happening one after another. It is a single fixed shape inside a frozen four-dimensional structure. The overwhelming sensation of moving forward, of the present sliding into the future, is something that shape produces because it can only ever read one cross-section of itself at a time. You're not going anywhere. In the deepest sense the mathematics allows, you have never been going anywhere. The entire length of your life, from your first breath to your last, already exists complete, and you are experiencing it the way the worm experiences the apple, one slice at a time, mistaking your own limited vantage point for the passage of time itself. But you do not feel frozen. That is the objection your whole body is raising right now, and it is a good one. You feel like you are moving. You feel the present as a live, moving edge. You remember yesterday vividly, and you do not remember tomorrow at all. And something about that difference, the sharp asymmetry between a past you can recall and a future you cannot, feels so fundamental, so obviously real, that it seems almost insane to question it. How can time not be moving when moving is the most basic thing it does? A physicist spent 30 years of his life on that exact question, and he came out the other side with an answer that sounds like it was engineered to keep you awake at 3 a.m. Part 7. 2 Ways the Ground Gives Out. Carlo Rovelli is an Italian theoretical physicist who spent 3 decades working on quantum gravity, on the problem of how to fit Einstein's smooth, flowing spacetime together with the jittery, uncertain world of the very small, and he came out the other side holding an answer that many people find genuinely difficult to sleep next to. Time, Rovelli argues, is not fundamental. It is not built into the deep fabric of the universe the way space seems to be. It is not a coordinate, not a dimension, not a direction. It is a story your brain tells itself, and it tells that story because your brain is limited in a very specific way. Here is what he means, and it is subtler than it first sounds. The 2 deepest descriptions of reality we have, quantum mechanics and general relativity, when you write them in their most fundamental forms, do not contain a variable for time the way you experience it. They describe relationships between things. This is correlated with that. This state is entangled with that state. This configuration goes with that configuration. But they do not, at the deepest level, single out a before and an after. They do not say which came first. The before and after, Rovelli says, is something you add. And you add it because your brain is a thermodynamic engine running on chemical gradients, and chemical gradients only flow in one direction, from concentrated to dispersed, from ordered to disordered. Think of a sugar cube dropped into a glass of water. It dissolves. The sugar spreads out until it is distributed evenly through the glass. And it never, ever reverses. You will never see the dissolved sugar spontaneously gather itself back into a cube. And here is the strange thing Rovelli wants you to notice about that. Nothing in the fundamental laws forbids it. The individual molecules of sugar and water are just bouncing around, and every one of those little collisions is perfectly reversible. Filmed up close, a single collision looks the same, played forward or backward, and you could not tell which was which. It is only when you zoom out to the whole cube, the whole glass, that a direction appears. The forward direction is simply the overwhelmingly more likely one. There are countless ways for the sugar to be spread out, and only a very few ways for it to be gathered into a neat cube, so spreading out is what you almost always see. The arrow, in other words, is a matter of counting, not of law. It emerges from your coarse, zoomed-out view of a world that, examined molecule by molecule, does not care which way time runs. Your neurons work the same way. Your memories form in the direction of increasing disorder, laid down like footprints that only point one way. That, Rovelli says, is the entire reason you remember the past and not the future. Not because the past is fundamentally different from the future in the structure of the universe. Because your hardware only writes in one direction. A camera that can only record and never rewind will eventually convince itself that the world only moves forward. But the world in this picture is not moving at all. The tape is simply stuck on play. Rovelli has a haunting way of putting it. Time, he suggests, is what ignorance feels like from the inside. If you could somehow see every particle in the universe at once, and track every interaction simultaneously, the distinction between past and future would simply vanish. There would be no flow, no direction, no before and after. There would only be a vast web of correlations hanging in silence. You experience the flow of time because you are too small, too local, too limited to see the whole picture at once. The flow is not out there in the universe. The flow is in your blindness, and that should unsettle you. But there is a version of this that is, in its own way, worse. Lee Smolin is a Canadian theoretical physicist, and he disagrees with Rovelli on almost everything that matters here. Smolin has spent his career arguing that time is not an illusion at all. It is the opposite. It is the most real thing there is, more real than space, more real than matter, more real even than the laws of physics themselves, and that last claim is the one that should keep you up at night, because if Smolin is right, then the laws of physics are not eternal. They did not exist before the universe, waiting for it to begin, and they will not necessarily outlast it. They were born with the Big Bang, the same way stars and galaxies were born. And like stars and galaxies, they can change, they can evolve. The speed of light might not have always been exactly what it is now. The strength of gravity might drift, imperceptibly, across trillions of years. The rules that hold your atoms together, in Smolin's view, are not carved into the bedrock of reality. They are more like weather. They are conditions that happen to be stable right now, the way the climate of the Earth happens to be stable right now. And like a climate, they could, in principle, tip into something unrecognizable. Without any warning, we would be able to read in advance. Feel the difference between these two answers, because it matters. Ravelli says time is an illusion produced by your limited perspective. That is uncomfortable, but it is static. Nothing changes. The block just sits there, complete, and you are frozen inside it, mistaking your own motion for the world's. Smolin says the block does not exist. Time is real. Time is fundamental, and precisely because time is real, nothing is permanent. Not the constants, not the forces, not the architecture of the atoms that make you. In Smolin's universe, you're not frozen inside a safe, unchanging structure. You're riding a wave that is reshaping itself as it moves, and you have no guarantee that the shape it takes tomorrow will still support the delicate chemistry that keeps you alive. One picture takes away your future, the other takes away the ground. And the question the data at CERN is quietly forcing into the open is which one of these two men is closer to the truth. Is time the frozen structure Minkowski described, where everything already exists and nothing genuinely changes? Or is time the only real thing, the engine underneath everything, rewriting the rules as it runs? Both of those answers, though, live in the large-scale world. Relativity, cosmology, the behavior of space and time across billions of light-years. But the anomalies at the collider are not large-scale. They happen inside a space smaller than an atom, over duration shorter than a trillionth of a second. To understand what is going wrong at those scales, you have to turn and look at the other half of physics, the half that has been quietly screaming something impossible for 100 years, while most of us went about our lives pretending not to hear it. Part 8. The particle that went through both. In 1801, a British scientist named Thomas Young set up what looks, on paper, like the simplest experiment in the history of physics. He took a beam of light and aimed it at a barrier with two narrow slits cut into it. Behind the barrier he placed a screen, and he watched to see what pattern the light would make. If light were made of particles like tiny bullets, you would expect something obvious. Two bright bands on the screen, one directly behind each slit where the bullets landed. That is what bullets do. Young saw something else. He saw an interference pattern, alternating bands of bright and dark, many of them, striped across the screen, and that is precisely the pattern you get when two waves overlap. Where the crests of two waves meet, they reinforce and you get brightness. Where a crest meets a trough, they cancel and you get darkness. Ripples on a pond do this. Sound does this. Young had shown that light was a wave, and for about a century that settled the question. Light was a wave, and waves do wave things, and everyone moved on. Then, in the early 1900s, physicists gained the ability to run the experiment in a new and much stranger way. Instead of a beam, they fired individual particles, one at a time. A single electron, launched like a lone bullet toward the two slits, then another, each one released only after the last had landed. Now a single particle cannot interfere with itself. A wave needs to overlap with another wave to make an interference pattern, and a single lonely particle has nothing to overlap with. A single particle should simply go through one slit or the other and strike the screen in a single spot. And indeed, each individual electron did hit the screen in a single spot, one small point of impact, exactly as a particle should. But when they fired thousands of these single particles, one after another, and let the spots accumulate, the pattern that slowly emerged on the screen was the interference pattern. Bands of bright and dark, wave behavior, built up one solitary particle at a time, and there is only one way to produce that pattern. Each particle, on its own, had to go through both slits simultaneously and interfere with itself on the way to the screen. Not half of it through one slit and half through the other, the whole particle through both slits at the same time. I want you to understand that this is not a trick of statistics. It is not a flaw in the equipment or a subtlety of measurement that clever engineering could remove. It has been checked 10,000 ways. You're looking at a single object occupying two positions in space at the same moment and interfering with itself as though there were two of it. Physicists gave this condition a name. They call it superposition. And it is not some exotic edge case that only happens in special laboratories under impossible conditions. This is how reality behaves at the smallest scale anyone has ever managed to measure. Every particle in your body did this before it became part of you. In some sense, it is still doing it. If that disturbs you, you are in extremely good company, because it disturbed one of the men who built the theory so deeply that he tried to use it to prove itself wrong. Erwin Schrödinger was one of the chief architects of quantum mechanics. He wrote the central equation, the one that predicts, with breathtaking accuracy, how particles behave. His name is on the mathematics, and he hated what his own mathematics was telling him. So in 1935 he proposed a scenario designed to expose how ridiculous the whole thing became when you scaled it up. Put a cat in a sealed box. Inside the box, place a device linked to a single radioactive atom. If the atom decays, the device releases a poison, and the cat dies. If the atom does not decay, the cat lives. Now, quantum mechanics says that the atom, before anyone checks on it, is in both states at once, decayed and not decayed, in superposition. But the atom is linked to the device, and the device is linked to the cat, so the mathematics, followed honestly, says the cat is also in both states, alive and dead. Simultaneously, Schrödinger meant this as a reduction to absurdity. He was saying, in effect, look how insane this gets. A cat obviously cannot be alive and dead at the same time. Therefore the theory must be incomplete. There must be something missing. 90 years of experiments have gently and relentlessly proven him wrong. Every test physicists have thrown at superposition has confirmed it. The cat, it turns out, is not a paradox to be explained away. The cat is an accurate description of what reality actually does when you are not looking at it. And in the last few decades, that description stopped applying only to particles hidden in boxes. It started reaching out across entire cities in a way that should have been impossible. Part 9. No Wall. Between the Strange and the Normal. In 2022, the Nobel Prize in Physics went to a man who spent decades proving something even stranger than the cat. His name is Anton Zeilinger, and he worked with pairs of what are called entangled particles. Here is what that means. You create two photons together in a single event, so that they share a common origin. Then you separate them. You send them to opposite sides of a laboratory, then opposite sides of a city. In Zeilinger's most famous experiments, opposite sides of the Canary Islands, more than 100 kilometers apart. And here is the thing that broke everyone's intuition. When you measure a certain property of one particle, the other particle instantly takes on the corresponding state. Not after a delay. Not after a signal has had time to travel between them at the speed of light. Instantly, regardless of the distance separating them. Now, the obvious escape hatch, the reasonable person's first guess, is that the two particles simply agreed in advance. That when they were created together, they were each stamped with a hidden instruction, a secret code, so that they were always going to give matching answers, and no mysterious connection is needed at all. It is like a pair of gloves. If you put one glove in each of two boxes and mail them to opposite ends of the earth, then the moment someone opens one box and sees a left glove, they instantly know the other is a right glove. No magic. The answer was fixed from the start. A physicist named John Bell closed that escape hatch in 1964. He proved, with a piece of mathematics of almost unbelievable cleverness, that if the particles were carrying hidden instructions decided in advance, then the statistics of many measurements would have to stay within a certain limit. And then experiments, Zeilinger's among the most rigorous, went and measured those statistics. They break the limit. There is no secret code. There was no prearranged agreement. The correlation is real, it is immediate, and it cannot be explained by anything the particles carried away with them. And I want to be careful, because this is one of the most misunderstood facts in all of science. Entanglement does not let you send a message faster than light. It cannot be used to signal or to control anything at a distance, and every serious physicist agrees on this. When you measure your particle, you get what looks like a random result, and so does the person measuring the far one. It is only later, when the two of you compare notes, that the eerie perfection of the correlation appears. So this is not a walkie-talkie across the galaxy. It is subtler and stranger than that. It is a hint that two things we insist on calling separate, because they sit far apart in space, are somehow bound together at a level deeper than distance, sharing a single quantum state that space itself does not manage to divide. So what you're looking at when you look at entanglement is not two particles secretly texting each other faster than light. It is 2 points in space that are not as separate as they appear to be. The distance between them, at some level we do not fully understand, is not quite what you think it is. So superposition is real. Entanglement is real. Particles exist in multiple states at once, and they remain connected across distances that ought to make connection impossible. And here is where almost everyone reaches for the comforting thought, the one you have probably been holding on to for the last few minutes. This is the quantum world. Photons, electrons, objects so small that a single molecule looks like a continent standing next to them. None of this applies to your world. Your coffee mug does not exist in two places. Your car does not entangle with your house. There is a boundary, somewhere, between the quantum and the classical, between the strange and the normal, and you live safely, comfortably, on the normal side of it. That is the most reassuring idea in all of modern physics. It is also, as far as anyone has ever been able to find, wrong. In 1999, a physicist named Marcus Arndt, working with a team in Vienna, fired molecules of carbon-60 through a double slit. Carbon-60 is not a photon. It is a molecule made of 60 carbon atoms arranged in the shape of a tiny soccer ball. By the standards of the quantum world, it is enormous, a lumbering giant. And it produced an interference pattern, the same pattern the single electron produced, the same pattern that can only mean the molecule went through both slits at the same time. The whole molecule, 60 atoms, through both slits. Since then, the record has been broken again and again. Molecules built of more than 2,000 atoms have shown interference. Mechanical oscillators, tiny engineered objects cooled to near absolute zero, have been coaxed into superposition. Even the LIGO gravitational wave detector, an instrument with mirrors that weigh around 40 kilograms, registers quantum behavior in those 40-kilogram mirrors. The boundary between quantum and classical, it turns out, is not a wall. It is a fence, and it is a fence that physicists keep dragging further and further back into larger and larger objects. And every single time they push it, they find more quantum on the other side. No one has ever found the point where quantum stops and classical begins, the line where the strangeness ends and the ordinary world takes over, because that point does not appear to exist. There is no border. There is no safe side. The quantum world is not a separate reality tucked away at the bottom of the size scale, operating under different rules. It is, as far as we can tell, the only reality. The solid, stable, sensible world you live in, the world of coffee mugs and car keys and concrete floors, is what happens when the quantum world loses something. Something leaks out of the system, and the strangeness quietly fades, and everything begins behaving the way you expect it to. The question, the one that opens the next door, is simple to ask and very hard to answer. What leaks, and where does it go? Part 10. What leaks, and where it goes. What leaks is information. A physicist named Wojciech Zurek spent 30 years working out the mechanism, and he gave it a name that has since become one of the most important words in this whole story: decoherence. Here is how it works, and it is worth going slowly, because this is the machinery that builds the ordinary world out of the strange one. A particle in superposition, existing in multiple states at once, is not fragile in the way you might expect. It does not need a conscious observer to knock it out of superposition. It does not need a scientist pointing a detector at it, or a mind noticing it. All it needs is contact. The moment a particle in superposition touches anything at all, a single photon bouncing off it, a stray molecule of air drifting past, a faint vibration in the ground beneath the experiment, information about its state begins spilling out into the environment. And it does not spill all at once. It bleeds. Each little interaction carries away a tiny piece of the picture. One molecule of air bumps the particle, and now that molecule carries a trace of which state the particle was in. Another molecule bumps that one, and the trace spreads a little further. Within a fraction of a second, the information about the particle's superposition has bled into so many surrounding particles, so thoroughly scattered, that no instrument you could ever hope to build would be able to gather it all back together. And this is the crucial, unnerving point. The superposition is not gone. It has not been erased. It has been diluted into the environment so completely that, from where you stand, it has become unreadable. Think of yourself sitting in a car with the radio dial locked to a single station. The other stations did not shut down when you tuned in. They are still broadcasting right now. The waves are passing through the car this very moment, through the dashboard, through your hands on the wheel, carrying music and voices you cannot hear. You cannot hear them because the dial is locked, and you do not have the tools to unlock it. Decoherence is that lock. It does not destroy the other states. It does not reach in and choose one outcome while deleting the rest. It simply spreads the rest so thin, smears them so far across the environment that you lose all access to them. The coffee mug on your table is in superposition right now. Every particle in it is doing exactly what the electron did at the double slit. But the mug is in constant contact with the air around it, with the surface of the table, with the light falling on it from the ceiling, and the information about its other possible states has bled into trillions of environmental interactions faster than you could ever measure or track. You see one mug sitting in one place because you only have access to one channel. That is what Zurek proved. He showed, in precise mathematical detail, how the sharp, definite, single-outcome world you live in emerges naturally out of the blurry, many-outcome quantum world underneath. It is one of the genuine triumphs of modern physics, and it explains almost everything. Picture what this means for the room you are in. The air around you is not empty and still. It is a blizzard. Every cubic inch holds an almost countless number of molecules, and they are moving fast, hundreds of meters per second, colliding constantly, ricocheting off every surface, off your skin, off the walls, off each other, billions upon billions of times a second. And light is pouring through all of it, bouncing off everything, carrying away a record of exactly where each object is. To a single particle trying to hold on to its superposition, this is not a peaceful place. It is a storm of contact. Every collision, every photon, is another witness, another copy of the information leaking outward. That is why the large, warm, well-lit world you live in looks so stubbornly solid and singular. It is not that the quantum strangeness is absent here. It is that here, in the blizzard, the strangeness is measured and copied and broadcast so fast by so many witnesses that it is erased from your view before you could ever catch it. The only way physicists see superposition survive in a large object is to take that object into the cold and the dark and the near-perfect emptiness, to hush the blizzard, to remove the witnesses one by one. In the ordinary world, the witnesses never stop. But it leaves one question standing, and it is a question Zurek's mathematics can describe but cannot dissolve. If the other states are not destroyed, if they are only hidden, only smeared out of reach, then where are they? Because if decoherence does not delete them, they are still, in some sense, running. Somewhere. Every other version of the mug in every place it might have been, every other version of the particle, in every state it might have taken, every other outcome that could have happened but that you did not see. According to the mathematics, they did not vanish. They were not erased. You just lost the signal. And once you have followed the logic that far, you are standing at the edge of the single, most vertiginous idea in all of physics, an idea that one graduate student wrote down 70 years ago, that almost destroyed his career, and that the field spent half a century refusing to look at directly. Part 11. The Student Who Subtracted the Collapse. Hugh Everett III was a graduate student at Princeton in 1957. His advisor was John Wheeler, one of the most respected names in all of physics. And Everett looked at the equations of quantum mechanics and noticed something that should have been obvious, but that everyone around him had been trained to look past. The mathematics did not contain a collapse. Nowhere in Schrödinger's equation, the central equation of the whole theory, was there a rule that said superposition ends when someone looks at it. That rule had been added by hand. It had been bolted onto the framework by Niels Bohr and the physicists around him, because without it, the equations produced a result that everyone found deeply uncomfortable. They produced branches. Every quantum event that could go more than one way went every way. The electron that could pass through the left slit or the right slit passed through both, and the universe split along the seam. Not into two copies of the whole cosmos floating side by side in space, that is the cartoon version, and it is misleading. Into two branches of a single structure, each one perfectly real, each one containing a version of the experiment with a definite outcome, and each one invisible to the other, because decoherence had already smeared the information between them into unreadable noise. The many worlds were not far away. They were right here, overlapping, sharing the same space, unable to see one another. And this is the part people always miss about Everett. He did not add anything to the equations to get this result. He subtracted. He removed the collapse rule that Bohr had inserted, the extra clause that forced a single outcome, and without it the mathematics ran cleaner than before. Fewer assumptions, fewer special cases, just the Schrödinger equation, evolving without interruption, and the branches falling out of it naturally, like cracks spreading through glass under pressure. Wheeler, his advisor, loved the work. He also knew, with a heavy heart, that it would end Everett's career. And he was right. The physics community dismissed the thesis. Bohr's camp refused to seriously engage with it. Everett published a shortened, softened version, received almost no response, and left academic physics permanently. Think about the human weight of that for a moment, because it is one of the quiet tragedies of 20th century science. A young man, barely out of graduate school, saw something true, wrote it down, and was met with a shrug and a closed door. He took a job with the Department of Defense doing operations research. He never published another physics paper. He died in 1982 at the age of 51. His son found his body. And it was only about 30 years after the thesis had been buried that physicists started cautiously coming back to it. Not because they had softened toward Everett as a person, but because the experiments kept confirming what his mathematics had predicted. The branches were not a philosophical daydream. They were the default output of the most tested equation in the history of physics. Everett did not invent parallel realities. He simply stopped pretending they were not there. But a dead physicist's mathematics, however clean, is not proof. To make people take the branches seriously, you needed a machine. And in 1985, a British physicist at Oxford named David Deutsch built the argument for that machine, and then it took the world about 30 years to catch up to what he was saying. Deutsch asked a question so simple it sounds almost like a trick. Suppose a quantum computer solves a problem that would take every atom in the observable universe, working together, longer than the entire age of the universe, to solve by ordinary means. Where, he asked, is that computation actually happening? Not as a metaphor, physically. Where are the operations being performed? A classical computer solves a problem one step at a time. If the problem has 1 trillion steps, the computer takes 1 trillion steps. But a quantum computer does not work this way. It places its quantum bits, its qubits, into superposition so that each one exists in multiple states at once, and then it runs the calculation across all of those states together. The result is not simply faster processing, the way a faster car covers the same road in less time. It is processing that Deutsch argued could not physically happen inside a single universe. There are not enough particles, not enough time, not enough physical resources in the entirety of observable space to carry out the computation the ordinary way. And yet the quantum computer does it. It gives you the answer. The answer is correct. So where did the work get done? Deutsch's answer is as bold as it is simple. The work happened in the branches. The qubit in superposition is not doing many things in one universe. It is doing one thing in each of many branches, and the branches share their results through quantum interference before decoherence drives them apart. A quantum computer, in Deutsch's reading, is a machine that reaches across the boundary between branches and borrows computational power from versions of itself that you can never see, never visit, and never speak to, except through this one narrow channel of interference. And these machines are not theoretical. They exist, they run, they solve problems that the resources of this single universe cannot account for. Every time one of them runs, Deutsch would say, it is quietly drawing on something outside the visible world. Part 12. The Only Shapes That Hold. You might still be looking for an exit from all this. Maybe the branches are a convenient fiction. Maybe the quantum computer works for some reason nobody has figured out yet, and the branches are just a story physicists tell each other to make the mathematics feel intuitive. Sean Carroll would gently turn that around on you. Carroll is a theoretical physicist and one of the most visible modern defenders of Everett's framework, and his argument is not that branches are the nicest interpretation, or the most elegant, or the most comforting. His argument is that branches are simply what the equations produce when you do not add anything extra to them. Here is the logic, and it is worth holding carefully, because it flips the usual burden of proof completely upside down. The Schrödinger equation evolves the quantum state forward, smoothly, without interruption. It never stops. It never collapses. It never reaches in and picks one outcome over the others. If you trust that equation, and you add nothing else to it, you get branches. Every other interpretation of quantum mechanics, and there are several respectable ones, starts with that same equation and then adds a rule, or a mechanism, or a philosophical constraint specifically in order to get rid of the branches. The Copenhagen interpretation adds a collapse that happens upon measurement. Objective collapse theories add a brand new physical mechanism that has never once been observed. Pilot wave theory adds hidden variables and an extra guiding equation. Each of them grafts something onto Schrödinger's equation to force a single outcome. Everett grafts nothing. He trusts the equation as written, and he accepts what it produces. And so Carroll's point is that the burden of proof runs the wrong way in most people's minds. You do not need a reason to believe the branches exist. They are the default output. What you need is a reason to believe they do not exist, and in 70 years no one has produced one. Not for lack of trying. Every experiment ever designed to find the edge of quantum mechanics, to locate the exact point where superposition fails and the ordinary classical world takes over, has instead pushed that edge further out. The branches keep surviving every test. The equation keeps doing what it has always done, and we keep looking for a reason to ignore it. I want to be fair here. Many excellent physicists do not accept many worlds, and the debate is genuinely open. But it is not a fringe idea. It is one of the leading readings of the most successful theory we have. But if the branches are real, a fair question presses in immediately. Why do they look like worlds? Why do you wake up in a stable room with solid walls and a definite floor, instead of a smeared-out fog of every possible arrangement bleeding into every other? If reality is really a superposition of countless outcomes, why does your particular slice of it feel so crisp and coherent? The answer is in the seams, and Zurich's work has a name for it. He called it einselection, short for environment-induced superselection, and it is the reason reality has texture instead of static. Think of a sheet of glass struck by a stone. The glass does not shatter into a fine, uniform dust. It cracks along lines of structural weakness, along the places where the molecular bonds are just slightly weaker than their neighbours. The result is not random. You get shards with clean edges, definite shapes, recognizable pieces. Einselection does the same thing to the quantum state of the universe. When decoherence spreads the information outward, the superposition does not dissolve into an even, featureless blur. It fractures along the lines of least resistance, along the states that leak the least into their environment, the states that are most stable, that hold their shape while everything around them dissolves into noise. The states that leak the most fall apart first. What survives are branches. Stable, self-consistent, internally coherent branches, and they look like worlds precisely because they are the configurations that hold together under the constant pressure of environmental interaction. You do not see a blur, in other words, because blurs are unstable. They cannot persist. They fall apart the instant they touch anything. What persists is structure, clean edges, definite outcomes. The world looks solid and singular and real, not because quantum weirdness politely stops at some border between the small and the large, but because solidity is the only thing that survives decoherence at all. Everything else shatters, and the shards that remain have edges so clean that you mistake them for the whole. The branches are not chaos. They are the only shapes that hold, and once you understand that the walls between them are not welded shut, but built out of something as delicate as information, you can start to ask a dangerous question. What happens if you reach in and pull that information back out? Part 13. The Wall Made of Information. In 1982, two physicists named Marlon Scully and Kai Druhl designed an experiment that, on its face, should not have worked. They took the standard double-slit setup, the one where a particle goes through both slits and produces an interference pattern on the screen. Then they added a detector at each slit, a small device that records which slit the particle actually passes through. And here is the standard result, the one every physics student learns. The moment you know which path the particle took, the interference pattern disappears. Information about the path destroys the superposition. The particle stops going through both slits and picks one, and the striped pattern on the screen collapses into two plain bands. No interference, no mystery. Knowledge kills the effect. Scully and Druhl added a second step. After the detector records the path information, they erase it. Not hide it, not ignore it. Physically destroy the record so that the which path information no longer exists anywhere in the universe. And when the record is destroyed, the interference pattern comes back. The particle behaves, once again, as though it went through both slits, as though the measurement never happened, as though the branch that split off when the detector fired had quietly rejoined the branch it had split from. A team led by Yoon-ho Kim confirmed this experimentally in the year 2000, and the result is exactly as strange as it sounds. The branches are not welded shut, they can be reopened. If you remove the information that separated them, the separation reverses. The wall between the branches is not made of stone, it is made of information, and information can be erased. Read that again, slowly, because of what it implies. You deleted the record of the choice, and the choice stopped existing. Not the memory of the choice itself. The particle did not remember going through one slit and then get overruled. It went through both again, because the information that had forced it to choose was pulled back out of the universe. The wall between the branches is thinner than you think, and it responds to something as insubstantial as a record being kept or destroyed. And the wall has an even stranger property. It does not respect the direction you think time moves. In 1978, John Archibald Wheeler, the same man who had supervised Everett's thesis, proposed an experiment so unsettling that it took nearly 30 years before anyone could actually build it. He called it the delayed choice experiment. The setup is a variation on the double slit. A particle is fired toward two paths, and at the very end, after the particle has already passed through, you decide whether to measure which path it took or to erase that information and let the interference pattern form. You make the decision after the particle has completed its journey, and the result matches your choice. If you decide at the end to measure, the particle turns out to have gone through one path. If you decide at the end to erase, the particle turns out to have gone through both. A decision you make now determines what the particle did then, not what it appears to have done, what it did. The experiment was actually realized by Vincent Jacques and his team in the year 2007, and the results confirmed Wheeler's prediction exactly. You need to sit with that for a moment. This is not a reinterpretation of old data, and it is not a matter of perspective. A physical event that has already occurred changes its character based on a decision that has not been made yet, at the time the event happened. Now, physicists are careful here, and so should we be. This does not let you send messages into the past, and it does not let you change history in any way you could use. But it does mean that the story of what happened is not fully written until the relevant information is finally committed. The branches, it seems, do not only leak into each other across space, they leak across time. And there is one more experiment, the most delicate of all, that lets us catch the branches in the very act of forming. In 1988, a physicist named Yakira Haranov, working with David Albert and Lev Vaidman, figured out how to look at a quantum system without shattering it. Standard measurement is violent. You hit the system with enough energy to force a definite answer, and the superposition collapses. You get your result, but you destroy the thing you were looking at. A Haranov's method, which he called weak measurement, is different. You touch the system so gently that it barely notices you are there. Any single one of these feather-light touches tells you almost nothing, just a whisper. But if you repeat the whisper thousands of times, across thousands of identical systems, the whispers accumulate into a signal, and the signal shows you the superposition while it is still alive. Before the particle has been forced to choose, before decoherence has spread the information, it shows you the particle in both states at once, with measurable weight in each, not inferred after the fact from a pattern on a screen, but watched directly as it happens. You are, in a real sense, looking at reality before it has made up its mind. And now hold that image and turn back to where this whole story started, because every one of these experiments works on single photons, on tabletop benches, at tiny energies. CERN is not a tabletop. CERN operates at the energies of the first instant of creation, where the walls between the branches are at their very thinnest. Part 14. Looking at the wall from this side. Every experiment I have just walked you through works on single photons. Tabletop setups, lasers and beam splitters and mirrors bolted to an optical bench in a university basement. The energies involved are tiny. The particles are light. The effects are unmistakably real, but they are fragile, confined to systems so small and so carefully isolated that the rest of the world never notices them. Now, the Large Hadron Collider smashes protons together at energies that have not existed anywhere in this universe for 13.8 billion years. And at those energies, the rules of the game shift. Decoherence still operates, it always operates, but the systems are so energetic and so violently compressed that the window between superposition and decoherence narrows to almost nothing. The branches have less time to separate. The wall between them, in a real and calculable sense, is thinner at high energy than it is at low energy. And the anomalies the detectors have been catching since the early 2020s sit exactly in that window. The B-meson tilt, the matter-antimatter asymmetry that outgrew its container, the bumps that flicker at the same energies in two independent detectors. Every one of them involves particles behaving as though more than one version of the outcome is pressing against the measurement at the same time, as though the branches, at the moment of collision, have not fully separated, as though the wall, at those energies, is thin enough for something on the other side to leave a faint mark on the data. I have to be careful and honest with you here, because this is exactly the moment where the honest version of the story and the exciting version part ways, and I promised you the honest one. Nobody at CERN has announced that they detected another universe. That is not what the papers say, and it is not what any responsible physicist claims. What is true is narrower, and in some ways stranger for being so restrained. There are anomalies. They are real. They sit at the energies where the mathematics says the branches are least separated, and the many worlds reading of quantum mechanics offers a natural language for what such anomalies could be. That is a very different thing from proof, and I will not pretend otherwise. But hold the shape of it together in your mind. The quantum eraser showed you that branches can rejoin when information is destroyed. The delayed choice experiment showed you that branches leak across time. The weak measurements let you watch the branches forming in real time, before they separate. And CERN is the only machine on Earth that operates at the energies where all three of those effects would be pushed from single photons up to the scale of the early universe. You have been looking at the wall this entire time. You just did not know that was what you were seeing. Imagine for a moment that you're standing in the control room, late at night, long after the visitors and the cameras have gone home. The collision data is scrolling past on the screens, more of it than any human could ever read, most of it perfectly ordinary, exactly as predicted, tick after tick after tick. And then, buried in one corner of one display, a single distribution leans the wrong way, just barely. You have seen it before. You saw it last month, and the month before that, always in the same place. You could call a colleague, you could point at it, but you already know what they will say because you have said it yourself 100 times. It is not 5 sigma. It could still be nothing. Come back when it is real. And so you sit there, alone with a number that is too small to announce and too stubborn to forget, that leans in the same direction every single time, and you feel the particular loneliness of being the first person to notice something that you cannot yet prove. That is where this field actually lives right now, not in a press conference, in that quiet room, watching a tilt that will not go away, waiting for the universe to either take it back or make it undeniable. But knowing what you're looking at does not tell you why you are looking at it from this particular side. The branches, if they are real, are all real. Each one contains a version of the experiment, a version of the room, a version of you. So which one is you? What picks this version of the outcome and not that one? What determines that you are the version sitting here right now, following these words, instead of the version in the branch next door who got up an hour ago and is somewhere else entirely, thinking about something else, living a life that diverged from yours at some quantum fork you never even noticed? For most of the last century, the most popular answer to that question in physics was essentially do not ask. And that answer was not laziness. It was a considered position, and it came from the two men who built the foundations of quantum theory. And to understand why the modern anomalies are so destabilizing, you have to understand exactly what those two men decided to leave in the dark, and why the darkness held for so long, and what finally dragged a lamp into it. Part 15. Who counts as the one who looks? Niels Bohr and Werner Heisenberg built that answer in Copenhagen in the late 1920s, and it became the default position of an entire field for generations. The Copenhagen interpretation does not tell you what happens when no one is looking. It tells you that the question is meaningless. Reality, according to Bohr, does not have a definite state until it is measured. Before measurement, there is no particle sitting at a position, no spin pointing up or down, nothing to talk about. The mathematics gives you probabilities, the measurement gives you a result, and the gap between the two, Bohr insisted, is not a mystery to be solved. It is a boundary you are simply not allowed to cross. There is a phrase that captured the spirit of this so well that it stuck like a brand. even though neither Bohr nor Heisenberg ever actually said it. Shut up and calculate. And it worked. For decades, it worked beautifully. Physicists used the recipe without ever asking what was cooking. They plugged numbers into the Schrödinger equation, extracted probabilities, compared them with experiments, and collected Nobel Prizes. The question of what was actually happening between measurements was not forbidden because it was dangerous. It was set aside because it seemed unnecessary. The recipe produced correct results every time. Why risk breaking something that worked so well by asking what it meant? For a practical working physicist, that was a perfectly reasonable bargain. The trouble is that the recipe has started giving answers it was never designed to handle. And it breaks in the most revealing way possible. It breaks when you point it at itself. In 1961, a Hungarian-American physicist named Eugene Wigner took the Copenhagen logic and pushed it one step further than Bohr ever intended to go. He imagined a friend inside a sealed laboratory, performing a quantum measurement. The friend measures a particle and gets a definite result. Spin up, let us say. From inside the lab, the experiment is over. The particle has a state. Reality has settled. But Wigner is standing outside the lab. He has not opened the door. He has not looked at the result. And according to the strict Copenhagen rule, a system that has not yet been measured does not have a definite state. So from Wigner's perspective, standing in the hallway, the friend, the particle, and the entire laboratory are one big quantum system that he has not yet observed. Which means, taken literally, the friend is in superposition. The friend has both seen spin up and seen spin down. The friend is in two states at once, and neither one becomes real until Wigner opens the door. Now you have a genuine contradiction. The friend says reality is definite. Wigner says it is not. Both are applying exactly the same rules correctly, and both arrive at incompatible answers. And there is no way to resolve the disagreement without answering a question that Copenhagen explicitly forbids you to ask. When does the measurement actually happen? Who counts as an observer? The friend observed the particle. Does that settle reality, or does Wigner need to observe the friend? And if someone else has to observe Wigner, the chain just extends another link. Observer, observing, observer, observing, observer, and it does not terminate. There is no final observer standing at the end. There is no place in the chain where you can plant a flag and say, here, this is where reality becomes definite. Everything before this was uncertain and everything after is settled. You cannot find that point because it does not appear to exist. For 60 years, the Copenhagen recipe let physicists ignore this by simply restricting the questions they were allowed to ask. Wigner had shown that the restriction was not a feature of nature. It was a crack, papered over with a rule that said, stop looking. And in 2019, a team of physicists stopped ignoring the crack, and they built the experiment. Massimiliano Proietti and his colleagues at Heriot-Watt University in Edinburgh constructed a real, physical version of Wigner's thought experiment using entangled photons. Not a simplified analogy, not a mathematical approximation. A physical system in which two observers could each make measurements on the same quantum event from their own reference frames and then compare their results. And the finding was exactly what Wigner's logic had predicted. The two observers obtained results that directly contradicted each other, not in the sense that they measured different values, but in the deeper sense that their measurements were logically incompatible. One observer's result could only be true if the other observer's result was false, and both results were physically valid, produced by legitimate measurements on real photons following real quantum mechanics. Neither could be dismissed as a mistake. The most careful way to state the finding is this. It does not prove that objective reality does not exist. What it proves is narrower and more precise, and honestly more unsettling for being so careful. It proves that if quantum mechanics is correct, and if the measurements are valid, then the assumption that all observers share a single, consistent account of physical events cannot be maintained. The two observers are not disagreeing about one shared world. Each is correctly describing their own branch, and the branches are incompatible. And if two observers standing in the same building cannot agree on what happened to the same photon, then a much larger and much lonelier question comes into view. What happens when you scale this up? Not to two people in a room, to everything. Part 16. The universe that never decided. The entire universe is a quantum system. It contains every particle, every field, every interaction that has ever occurred or ever will. And if quantum mechanics applies to individual photons, and to entangled pairs and to laboratory setups, then it applies to the whole structure. There is no reason it would stop. There is no size limit written into the equations, no line past which the rules quietly switch off. And if the whole universe is a quantum system, then the question Wigner asked about his friend applies to the cosmos itself. Who observes the universe? There is no one outside it. There is no door to open. There is no Wigner standing in the hallway, waiting to collapse the state of everything. In 1967, two physicists confronted this problem head-on. John Wheeler again, and Bryce DeWitt wrote down an equation that attempts to describe the quantum state of the entire universe. It is called the Wheeler-DeWitt equation, and it is one of the strangest objects in all of physics. Not because the mathematics is unusually complicated, but because of what the mathematics leaves out. The equation has no variable for time. The letter that stands for time simply does not appear in it. The most complete quantum description of the universe we have ever written down does not contain the one thing you feel most certain about, the passage of time. It describes a static object, a structure that does not evolve, does not change, does not move from one moment to the next, and it has no observer. And here is where two threads of this whole story tie together into a single knot. If collapse requires an observer, and the universe has no external observer, then the universe has never collapsed. The wave function of the entire cosmos has never snapped into a single definite state. It is still in superposition. Every possible configuration of matter and energy, every possible history, every possible version of every event that has ever happened, all of it coexisting inside a single timeless mathematical object, and you are inside that object. You're not observing it from the outside. You're a pattern within it, a pattern that generates the sensation of time, the sensation of definiteness, the sensation of being one person in one place at one moment, all from inside a structure that contains all places and all moments at once. The universe never decided. You are living inside the indecision. But you do not feel like you live inside indecision. You feel a direction. Yesterday is behind you, tomorrow is ahead, and the arrow points only one way. So if the universe is a timeless block with no time variable in its deepest equation, where does that arrow come from? This is one of the oldest and most stubborn puzzles in physics, and the answer is genuinely surprising. Nearly every fundamental law of physics is symmetric in time. Run Newton's equations backward, and the planets trace the same orbits in reverse, perfectly legal. Run the equations of electromagnetism backward, and the waves converge instead of spreading, perfectly legal. Run the Schrödinger equation backward, and the quantum states evolve in reverse just as smoothly as they run forward. None of these laws know the difference between past and future. None of them care, except one. In the 1870s, an Austrian physicist named Ludwig Boltzmann formalized the single rule that every other law of physics ignores, the second law of thermodynamics. It says that entropy, the measure of disorder in a system, tends to increase over time. A glass shatters on the floor, and the pieces never reassemble. Cream poured into coffee spreads out, and it never gathers itself back into a swirl. A fire burns wood into ash, and the ash never unburns. Every irreversible thing you have ever witnessed is the second law in action, and it is the only law in all of physics that distinguishes the past from the future, the only one. Every other equation runs the same in both directions. The second law plants a flag and says, "this way," and that flag is the entire reason you experience time as having a direction at all. Your memories form because laying them down increases entropy. Your body ages because the reactions inside it increase entropy. The arrow of time, in this view, is not a feature woven into the universe. It is a feature of one law, and that one law has a problem. It says entropy increases, disorder grows, systems slide from ordered toward disordered. That explains the direction, but it does not explain the starting point. If entropy is always increasing, then it must have been lower in the past. And if you follow that logic all the way back to the beginning, entropy at the birth of the universe must have been extraordinarily, almost unimaginably low. The universe must have started in a state of exquisite order. Roger Penrose actually tried to calculate the probability of a starting condition that ordered, and the number he produced is not like other numbers in physics. It is 1 divided by 10 to the power of 10 to the power of 123. If you tried to write that number out in ordinary form as a one followed by zeros, you would run out of universe before you ran out of zeros. There are not enough particles in all of observable space to write it down. The probability of the universe beginning in the state it actually began in is so vanishingly small that the word improbable does not even apply. Improbable means unlikely but possible, like drawing the same card 1,000 times in a row. This is past that, so far past it that the comparison breaks. Imagine every particle in the cosmos as a die, and imagine every single one of them, all at once, needing to land on exactly the right face for the universe to begin ordered enough to eventually make galaxies, and chemistry, and you. That picture still is not extreme enough, but it points in the right direction. The beginning of the universe was tuned, by nothing anyone can identify, to a precision that has no name and no analogy. And the arrow of time you feel every moment, the simple fact that you remember breakfast and not dinner, hangs entirely from that one unexplained, exquisitely ordered first instant. And yet, here we are. The entropy was low. The arrow exists, and for over a century physicists mostly just accepted that starting point as a brute fact, a given, something you write into the foundations by hand. Two philosophers of physics, David Albert and Craig Callender, even gave this act of acceptance a name. They called it the past hypothesis, not a law, not a derivation, a postulate, inserted because without it, nothing else works. The arrow of time, for 100 years, has rested on a patch, a placeholder where an explanation ought to be, and then someone asked whether the arrow might not come from the beginning at all, whether it might come from the branching. Part 17. Time as a tree, not a river. In 2017, Lev Vaidman, the same physicist who had helped develop weak measurements, published a paper arguing that the direction of time is not a consequence of low initial entropy at all. It is a consequence of the universe splitting. Every quantum event that has more than one possible outcome produces branches, and the number of branches only increases with every interaction. Particles collide and the outcomes multiply. Atoms decay and the tree of possibilities grows wider. The universe, in this picture, does not move from past to future. It moves from fewer branches to more branches, and that, Vaidman says, is the arrow. Not entropy climbing up from an impossibly ordered floor, but branching, spreading outward from every quantum event like cracks propagating through a windshield. A philosopher of physics named Janan Ismail extended this idea into a fuller framework. If the branching is real, then the increase of entropy is not the cause of the arrow. It is a side effect. Entropy increases because the number of branches increases, and more branches means more possible configurations, and more possible configurations is exactly what entropy measures. And the low entropy beginning stops being a mystery. It was low entropy because the universe had not yet branched. The tree had not yet grown. The trunk is narrow, not because someone carved it that way, but because it had not yet had time to split. You have been thinking of time as a river flowing from a source, and a river forces you to ask where the water comes from. Vaidman and Ismail say it is not a river, it is a tree growing from a seed. And a tree does not need someone to explain where it comes from. A tree grows because growing is what trees do. Each fork creates two paths, and each path forks again, and the direction you experience as forward is simply the direction in which there are more forks. You're not moving through time. You're riding the endless branching of a structure that cannot stop splitting. The sensation of the present is the feeling of being at the newest fork. The sensation of the past is knowing which forks are behind you. The sensation of the future is not knowing which fork comes next. Now, if reality branches at the smallest scale, and if that branching is deep enough to generate the arrow of time itself, you might expect the whole business to stay confined to the quantum world, to particles and atoms and effects too small to matter at the scale of stars. Cosmology says otherwise. In 1986, a physicist named André Linde proposed a model of the early universe called eternal inflation. Standard inflation theory says the universe expanded exponentially in the first fraction of a second after the Big Bang, and then slowed down and settled into the gentle expansion we see today. Linde's version says the inflation never actually stopped. Not everywhere. In most of the universe, that violent exponential expansion is still happening right now, stretching space faster than light can cross it. But in scattered pockets, the inflation slows, energy converts into matter, physics settles into stable patterns, and a pocket universe forms. And ours, Lind suggests, is one of those pockets. A bubble of calm inside an ocean of expansion that has been running for 13.8 billion years, and in this model will run forever. And here is the part that connects everything. Each pocket can settle into different physical constants, different particle masses, different force strengths. The speed of light in one pocket does not have to match the speed of light in another. The rules are local. They crystallized when the pocket formed, the way crystals freeze into different patterns depending on the temperature and pressure at the moment they form. So two entirely separate branches of physics, quantum mechanics and cosmology, built by different people using different mathematics, describing scales separated by some 60 orders of magnitude, arrived independently at the same conclusion. Reality branches. It branches at the quantum level through superposition and decoherence, and it branches at the cosmological level through inflation and pocket formation. Different mechanisms, different scales, the same answer. There is more than one version of everything. How many versions? Leonard Susskind, a theoretical physicist at Stanford who helped create string theory, once tried to count the number of possible universes that the mathematics of string theory allows. String theory describes the fundamental constituents of reality as tiny, vibrating strings whose behavior depends on the geometry of extra dimensions curled up too small to see. That geometry can take many shapes, and each shape produces a different set of physical laws. Susskind counted the shapes, and the number he arrived at is 10 to the power of 500. That is not a large number, the way a billion is a large number. A billion you can picture. 10 to the power of 500 breaks every analogy you could reach for. If every atom in the observable universe were itself a universe, containing as many atoms as ours, and every one of those atoms were also a universe, and you nested that 100 times over, you would still not reach it. Your universe, with its specific electron mass, its specific gravitational constant, its specific speed of light, is one configuration out of that unfathomable number. Not chosen, not designed, not optimized. One point on a landscape so vast that the word vast means nothing against it. The obvious response is, so what? You are here. Your universe has the right constants for stars and carbon and water. If they were different, you would not be around to notice, so of course you find yourself in a universe compatible with your existence. This argument has a name, the anthropic principle, and it is not wrong. But it is also not an answer. It tells you why you're not surprised to find the constants friendly. It does not tell you why a universe friendly to you exists in the first place. It is like standing in the one room in a huge building that happens to have oxygen and saying, I am here because this is the only room I could breathe in. That accounts for your location. It does not account for the room, and there is exactly one place on this planet that operates at the energies where the two kinds of branching, the quantum and the cosmological, might turn out to be the same branching, where the fork in the particle and the fork in the cosmos could be one fork. That place is the collider. It sits not at the quantum scale and not at the cosmological scale, but at the boundary between them, and the anomalies that started this whole conversation sit right on that boundary. Part 18, Made of Answers. That brings us to the deepest layer of all, the one that sits beneath the particles and the forces and the branches, beneath even the equations that describe them. It is a question not about what reality contains, but about what reality is made of. And the answer that a handful of the most serious physicists of the last century arrived at is not matter, it is information. In 1961, a physicist at IBM named Rolf Landauer proved something that should have changed the way everyone thinks about the universe, and that most people outside physics have still never heard. He proved that information is physical, not information in some vague, abstract sense, not data as a poetic idea, but physical information, subject to the laws of thermodynamics. Landauer showed that the act of erasing a single bit of information, flipping a 1 to a 0 with no record kept of what it was before, requires a minimum amount of energy. The energy is tiny. It is proportional to the temperature of the environment, multiplied by a fundamental constant of nature. But it is not zero. It cannot be zero. Erasing information produces heat. Storing information requires space. Processing information takes time. Information obeys thermodynamics in exactly the same way that matter does. Let that reorganize your picture of the world. You have been thinking of information as something that describes reality, a label you attach to a particle, a measurement you scribble in a notebook. Landauer proved that the label is as real as the particle. The measurement is as physical as the thing being measured. When the quantum eraser experiment destroyed the record of which slit the photon passed through, it did not merely change what the experimenters knew, it changed the physical state of the system. The information was not a description sitting outside the experiment, floating in some separate realm of facts. The information was part of the experiment, it was part of reality, and removing it changed what reality did. The particle went back to going through both slits. Erasing the record was a physical act with physical consequences, because information is not a shadow cast by matter. It is a thing in its own right, with weight and heat and cost. And if information is physical, then a question that used to sound like idle philosophy becomes sharp and urgent. Which is more fundamental, the matter or the information? John Archibald Wheeler, the same Wheeler who supervised Everett and who co-wrote the timeless equation of the universe, spent the last 2 decades of his life arguing that the answer is information. And Wheeler was not a marginal figure to be waved away. He was the man who named the black hole. He worked on the deepest problems in physics for half a century, and late in his life he proposed a principle so compact it fits on a bumper sticker. It from bit. Every particle, every force, every physical quantity in the universe, Wheeler suggested, derives its existence from binary choices, yes or no, spin up or spin down, here or there. The material world in this view is not the foundation with information painted on top of it. The information is the foundation, and the material world is what emerges on top. Think about it this way. You see a table, solid wood. You can knock on it. It holds your coffee. But the table is made of atoms, and the atoms are made of smaller particles, and those particles are described entirely by quantum numbers, discrete values that answer binary questions about spin and charge and position and momentum. Strip away the quantum numbers, and there is nothing left underneath. No substance behind the mathematics, no stuff hiding behind the numbers are the stuff. Wheeler's claim is that the universe is not a machine running on some material substrate. It is a vast network of binary answers, with no substrate beneath it at all. Every physical thing, every it comes from a bit, a piece of information. The table exists because certain questions were answered. The coffee exists because certain questions were answered, and you exist because a specific, staggering sequence of binary questions, stretching all the way back to the first instant of the universe, was answered in a specific order that eventually led to carbon and water and neurons, and the particular arrangement of matter that calls itself by your name, not answers recorded on some material, answers that are the material. In Wheeler's picture, you're not, at the deepest level, made of atoms. You're made of answers, and Landauer's proof gives that poetic-sounding idea a hard, physical edge. Because if every bit of information carries a real minimum cost, then a universe made of information is a universe that must, in some sense, keep a budget. Every fact that gets recorded takes energy and space. Every fact that gets erased releases heat. This is not a metaphor, and it is not philosophy. It has been measured in the laboratory. Physicists have built experiments delicate enough to detect the tiny puff of heat released when a single bit is erased, and it lands exactly where Landauer said it would. Think about what that implies. When you form a memory, the universe pays a thermodynamic price for it. When you forget, another price is paid. The bookkeeping of information is woven into the same thermodynamics that runs the stars and cools your coffee and drives the arrow of time itself. Information is not something we invented to talk about the world. It is one of the currencies the world is actually built out of. And once you have followed physics all the way down to that floor, a question that people usually laugh off suddenly stops being funny. Part 19. The Question That Dissolves. In 2003, a philosopher at Oxford named Nick Bostrom published a paper that, despite its reputation, does not actually argue that we live in a simulation. That is the version that got passed around and flattened. What the paper actually says is simpler and much harder to shrug off. Bostrom constructed a trilemma, 3 statements, at least one of which must be true, with the logic connecting them tight enough that you cannot easily escape. Statement 1. Virtually all civilizations at our level of development go extinct before they reach the computational power required to simulate conscious minds. Statement 2. Virtually all civilizations that do reach that power choose, for whatever reason, never to run such simulations. Statement 3. We are almost certainly living inside a simulation. You do not get to reject all 3. The structure of the argument forces you to accept at least one of them, because if advanced civilizations tend to survive, and if they tend to run simulations, then the number of simulated minds would vastly outnumber the original biological ones. And if you are a conscious being with no way to tell which kind you are, the odds would overwhelmingly favor simulated. Not by a little. By a margin so large that the probability of being an original rounds to nothing. Most people reject Statement 3 on instinct, and that is fine, but rejecting it means betting everything on Statement 1 or Statement 2. Either civilizations reliably destroy themselves before crossing that threshold, or they reliably choose not to use a power they possess. Neither of those is comforting. Neither can be checked. And notice that this argument has nothing to do with faith or mysticism. It is probability theory applied to the nature of observers, and in more than 20 years, no one has found a clean error in the reasoning. 2 of the 3 doors lead somewhere you do not want to go, and you are required to walk through one of them, unless the question dissolves. And this is where every strand of this long story finally braids together. If reality is fundamentally information, and if the universe branches, then every concept you have wrestled with tonight maps cleanly onto a single frame. Superposition stops being a particle magically being in 2 places at once. It becomes a computation running 2 processes in parallel. The double slit stops being a paradox. It becomes a system evaluating both paths at the same time and producing a combined output. Decoherence stops being a mysterious collapse triggered by a mind looking. It becomes resource management. The system tracks every interaction, and when the information about one branch has spread into too many environmental variables, the cost of maintaining coherence between the branches exceeds the benefit, and the system simply lets them diverge. It stops tracking the correlation. Not because something magical happened, but because continuing to track it would cost more than the result is worth, and the observer in this frame stops being a conscious mind peering at a particle and somehow forcing it to choose. The observer becomes the moment when the system commits its resources to one branch and releases the other. You're not a user sitting outside the program watching it run on a screen. You're a process inside the program, a subroutine that generates the experience of continuity, the experience of time, the experience of being a single self in a single world, because that is exactly what the architecture of decoherence produces. A process that can only ever read its own thread. Every anomaly in quantum mechanics that we have walked through becomes expected behavior the instant you describe reality as a system managing information under constraints. The quantum eraser works because deleting the record of which path was taken removes the flag that told the system to keep the threads separate. The delayed choice experiment works because the system does not finalize which branch you are on until all the relevant information has been committed. The weak measurement works because you can sample a thread gently, without forcing the system to commit, and the collider works at energies where the thread management itself starts to break down, where the flags blur, where the system is processing so much information, packed into so small a space that the boundaries between the threads begin to leak. I want to be honest that this is a picture, a way of seeing, and not a proven theorem. Not every physicist would sign their name to it, and the word simulation carries baggage it does not deserve here. It does not require a programmer, or a server, or anyone watching. It only requires that information is what reality is made of, and that the mathematics we already trust be taken at its word. But if you do take it at its word, then the strangest results in all of physics stop being a museum of impossibilities and start looking like the ordinary behavior of a system doing exactly what such a system would do. You're not watching the universe from outside. You are a thread inside a system that is deciding right now which threads to keep running. And that reframes the very last thing, the thing you have been quietly afraid of this whole time, the wall. Part 20. The Load-Bearing Wall. You have been thinking of decoherence as a limitation this entire time, a barrier, a wall between you and the other branches that better instruments, higher energies, and smarter experiments will eventually let you break through. But Zurich's work on Einzellection points to something almost opposite. Einzellection is not a limitation. It is a filter, and it is a generous one. It selects the states that can persist. Out of an unimaginable number of possible quantum configurations, the overwhelming majority are unstable. They fall apart the instant they touch anything. They cannot hold a shape. They cannot sustain a pattern. They cannot support structure of any kind. Einzellection strips all of those away. What survives is the narrow set of states that can resist environmental interaction long enough to become real, in the only sense of that word that matters to a creature like you. Atoms, molecules, tables, stars, you. Without einselection, there is no structure, there is no chemistry, there is no time in any sense you could experience, there is only noise, every possible state of every possible particle, all existing at once, with no hierarchy, no persistence, no difference between one configuration and the next. A television tuned to every channel simultaneously is not showing you more information, it is showing you less. Static contains every possible image superimposed into nothing at all. Einselection is the tuner. It is the mechanism that pulls a single clear signal out of that infinite static, and the signal it pulls out is the one you call reality. So turn the whole picture over one last time. You have been thinking of the wall between the branches as the thing keeping you from seeing the full picture. But the wall is the picture. Without it, there is nothing to see. Decoherence is not keeping you from the truth. Decoherence is the only reason there is a truth to keep. It is not a barrier standing between you and some larger, fuller reality. It is the load-bearing wall of the entire building you are standing in. Every floor, every room, every structure in that building exists because that wall is holding, and the collider is pressing against it with more force than anything in the history of this planet. That force, and this is the last piece of physics in the story, is not gentle. It is not passive. A measurement at the energies the collider reaches is not observation, the way a telescope observes a distant star, quietly gathering light that was already on its way. In 1958, two Soviet physicists, Lev Landau and Evgeny Lifshitz, whose textbooks trained half a century of physicists, formalized a principle that most people outside the field have never encountered. Measurement is irreversible. When you measure a quantum system, you do not passively read its state. You interact with it. You change it. You entangle your measuring device with the system being measured, and that entanglement cannot be undone. The information you gained is not a copy you can throw away. It is a link, a physical connection between your instrument and the thing it touched. Before the measurement, the system and the instrument were separate. After the measurement, they share information. They are correlated, and that correlation is permanent. You cannot unmeasure. You cannot put the information back. The system has been altered by the very act of coming to know about it, and that alteration ripples outward through every interaction that follows, like a wave that never quite dampens. Now hold that against what the collider actually does. It does not measure particles the way a thermometer measures the temperature of a room. It smashes protons together at energies that recreate the first instant of creation. It brings into being particles that have not existed for 13.8 billion years, and it entangles its detectors with the products of those collisions. If those products carry any trace of the branches pressing against each other, if the anomalies are even partly what the many worlds reading suggests they might be, then the collider has not merely observed the wall between the branches from a safe distance. It has touched it. It has entangled our instruments with whatever sits at that boundary. And that entanglement, by Landau and Lifshitz's principle, cannot be undone. You did not look through a window. If the strongest reading is right, you opened a door, and you cannot close it, because closing it would mean destroying the information you gained, and the information has already spread. Into the detectors, into the computers, into the papers, into this very sentence you are hearing right now. The connection is made, and connections like this do not unmake themselves. So this is where the honest version of the story leaves you standing. Not with a monster, not with an invasion, but with a crack, running through the most successful theory ever built, at the one place where the branches lie closest together, growing a little wider with every collision. Not because the machine is powerful, but because the act of knowing is itself the pressure. The wall does not care about our intentions. It does not distinguish curiosity from harm. It only registers that information has crossed from one side to the other, and that the crossing is permanent. Before you carry that home with you, though, I want to stop, and I want us to breathe, because there is one more thing to say, and it is the most important thing of all. Part 21. Be the part that notices. Everything you have just heard is a model. Every equation, every interpretation, every framework that describes branches and walls and cracks is a human construction, built to make sense of a handful of data points on a screen. And I want to hold that line very clearly, because it is where honesty lives. The data is real. The mathematics is real. The anomalies are real. but the story we wrap around them is ours. We built it the way we build every story, out of pattern recognition and metaphor and the deep, ancient human need to make the incomprehensible feel like something we can hold in our hands. The universe does not owe us a shape we can understand. It does not owe us an answer that fits inside a sentence. It does not even owe us the comfort of knowing whether the wall is real or the branches are real or the crack matters at all. What it owes you is nothing, and that is not a tragedy. That, I think, is the point. Because you are a specific configuration of matter, sitting in a specific place, in a specific branch of whatever this structure turns out to be. You're not an abstraction. You're not a probability cloud. You're not a thread in a system waiting to be deallocated. You're a person who breathes and eats and forgets where they put their keys, who laughs at things that are not that funny, who lies awake sometimes wondering whether any of it means anything. And here is what the physics, underneath all the vertigo and all the mathematics, actually leaves you with. Out of every possible arrangement of matter, out of every branch and every fork and every quantum event that could have gone another way, this specific configuration exists. The one that contains you, not a version of you, the one hearing these words right now. The probability of your exact configuration is so small that it makes even Penrose's impossible number look generous. And yet, here you are. Not because the universe chose you, not because a simulation selected you, not because some observer collapsed a wave function in your favor. You're here because the structure of reality, whatever it is, permits you, and that permission is not something you have to earn or justify or fully understand. It is something you already have. Every branch of physics we have walked through tonight, from the collider to the block universe to the branches to the wall, describes a structure so vast and so indifferent that your existence inside it should be impossible. But you are not impossible. You are actual. You are the part of the structure that woke up and started asking what the structure is. And no equation, however complete it ever becomes, will be more remarkable than the fact that something inside the mathematics learned how to ask about the mathematics. The branches may be real. The wall may be thinning. The crack may be growing, a little wider with every collision beneath that quiet field in Europe. None of that changes the fact that right now, in this specific slice of this specific branch, you are here. You are conscious. You are turning these ideas over in a mind that exists. And that means this branch, whatever else it is the one where someone is paying attention. There is an old fear buried under everything we have talked about tonight, and it is worth naming plainly, because naming it is how you set it down. The fear is that if all of this is true, if you are one slice of a branching structure, one thread in an information system, one improbable configuration among an unthinkable number, then you do not really matter. That you're small and replaceable and lost in the arithmetic. But turn the number over and look at the other face of it. Every one of those staggering figures, the 10 to the power of 500 universes, the branches multiplying at every fork. The impossible odds against your exact arrangement of matter does not make you smaller. It makes you rarer. It means that the particular pattern that is you, your specific memories, the specific sound of your specific name in your own head, occurs in a vanishingly thin sliver of everything that could have been. You're not common, you're not repeatable. In the whole enormous ledger of the possible, this exact you appears almost nowhere. And it appears here. That is not a reason to feel lost. That is as close to a miracle as physics is ever going to hand you. The universe is vast and possibly branching, and possibly computing, and quite possibly indifferent to everything inside it. But you are not indifferent. You cared enough to wonder. You stayed with a hard, strange idea all the way to the end of it. And in a structure that may contain every possible version of every possible outcome, the version that contains someone who cares is the one worth being in. So do not be afraid of the wall. Do not be afraid of the branches. Do not be afraid of the crack. Be the thing that the structure cannot produce on its own. Be the part that notices. Be the part that asks. The equations will keep running whether you understand them or not. The collider will keep firing. The data will keep arriving, one collision at a time, one decimal place at a time. The wall will do whatever the wall does. But none of it means anything until someone stands inside the structure and decides that it matters. Tonight, in this branch, that someone is you. Rest easy. The strangeness will still be here in the morning, patient as ever, and so, quietly and improbably and completely will you.